Our cosmos began 14 billion years ago with a big bang, and it has been expanding ever since. When you look up in a clear sky, there are stars everywhere, and you almost feel like you're in the middle of the universe. You believe you are the center of the universe from the moment you are born. The Earth was believed to be the center of the universe, with the Sun and all other planets orbiting around it by early humans. However, it has now been shown that we are not even in the center of our own solar system. Edwin Hubble discovered in 1929 that things farther away from Earth were moving faster. To put it another way, the cosmos has to be growing. But how did Hubble figure out that the universe was expanding? And where is the universe's center? Keep on watching to find out. So, how did Edwin Hubble figure out that the universe was expanding? Most astronomers thought our whole universe was made up of only one galaxy, our own Milky Way, a century ago. Hubble was one of the first to notice that there is a universe of galaxies beyond our Milky Way galaxy in the 1920s. What an awe-inspiring discovery. Edwin Hubble spotted stars in a hazy area of light known as the Andromeda Nebula at the time. Hubble was particularly interested in variable stars, or stars that alter brightness. He calculated the time it took for a star to dim and brighten. He calculated the star's intrinsic brightness using the brightening period. He was able to compute the distance using this information. That's when he discovered the stars in this nebula were so far apart that they couldn't possibly be in our galaxy. Many scientists thought the Andromeda Nebula was a budding solar system within the Milky Way's boundaries at the time. This area of light turned out to be a separate galaxy, as Hubble discovered. We now recognize it as the Andromeda Galaxy, thanks to Hubble. Beyond the Milky Way, it is the nearest big spiral galaxy. Thanks to Hubble, astronomers were able to determine that we live in an expanding universe, in which one galaxy is moving away from the next. For many years, Hubble's law was the name given to this finding. In its most basic form, the rule asserts that the further a galaxy is from us, the quicker it moves away from us. This is the core of our modern cosmology. A Big Bang is supposed to have created the whole universe, including space, time, and matter. Now that we know the cosmos is expanding, where is the universe's center? The universe appears to be the same despite which direction we look or how far away our telescopes and sensors can view. The number of galaxies, the sorts of galaxies present, the populations of stars that live inside them, the concentrations of normal and dark matter, and even the temperature of the radiation we observe are all uniform, regardless of which direction we look. The average difference between any two places on the biggest of cosmic scales is about 0.003%, or around 1 part in 30,000. The main differences we see aren't caused by the direction we look, but by how far away we look. The further away we look, the further back in time we view the universe, and the more light from distant objects is pushed towards longer wavelengths. Many people have a certain image in their thoughts when they hear this: the higher the quantity of light shifted, the quicker these items move away from us. As a result, the center of the universe may be found by looking in all directions and calculating at what point in space would we see all directions fading equally. The waves emitted by moving objects look compressed, with their crests and troughs closer together, as most of us know instinctively. Similarly, when they travel away from you, the waves look rarefied, with their crests and troughs spaced more apart than if they were stationary. Although we usually associate this with noises, as you can determine if a fire engine, a police car, or an ice cream cart is approaching or fleeing from you based on its pitch, it applies to any wave, even light. The Doppler Effect, named after its discoverer, is a motion-based shift of the waves. When it comes to light, however, a change in wavelength does not equal higher or lower pitches, but rather greater or lower energy. In the case of light, lower frequencies, lower energy, and redder colors are associated with longer wavelengths. Greater frequencies, higher energy, and bluer colors are associated with shorter wavelengths. Because of the nature of matter in the universe, there will be atoms and ions present in each particular thing that we measure. All atoms and ions produce and/or absorb light at certain wavelengths, so if we can figure out which atoms are there and detect a systematic shift in these spectral lines, we can figure out how red-shifted or blue-shifted the light is. Because of this, the further an object is from us, the larger the observed redshift. Is this because when an item produces light, it moves through space relative to us, yet when we absorb and measure light, it does not? Is it because the universe is expanding on a grand scale, causing light to continue to move along its long journey across the space that separates us from what we're attempting to observe? As light travels through space, the impacts of space evolution imprint themselves on the qualities of the light that will eventually reach our eyes. The fabric of space is changing, causing light passing through it to shift systematically, while galaxies and other light-emitting objects in the universe are moving across that changing space, creating motion-dependent changes. The evidence not only points to a universe that is expanding, but the projected method that the universe is expanding amazingly conforms with the predictions of general relativity for a uniformly filled universe with diverse types of matter and energy, as originally noticed in the late 1920s. General relativity's formulas are entirely predictive once you understand what your universe is made of and how this is expanding nowadays. We can start figuring out what the universe would be like in terms of size, separation distance, and instant expansion rate at every point in its old days, and what it will be like at every point in our future. If this is the case, the expanding universe isn't at all like an explosion, which has a point of origin from which everything, like shrapnel, travels outward at different speeds. The sole advantage of our placement in space is that the objects we see close by are the oldest and most advanced objects we can see today, while the items further away are younger. The expansion rate in the immediate vicinity is currently lower than the expansion rate seen at larger distances. In addition, the light from the nearest objects is less redshifted, and its shifts are less dominated by the cosmic component of redshift than the light from the furthest objects. That's because the objects that exist everywhere around the universe can't send messages faster than light, and the light we see from them now relates to light that's coming right now but must have been produced a long time ago. However, if we wanted to know where, from our perspective, all directions genuinely seemed as completely uniform as possible, we could look at the cosmic microwave background, which is leftover radiation from the Big Bang. As a result, the cosmic microwave background can assist scientists in piecing together the universe's past. Material bursts outward from a center point in a conventional explosion. The center of the explosion will be the hottest area for a short time after it begins. A circular shell of material will form later, extending out from the center until gravity pulls it back down to Earth. As far as we can tell, the Big Bang was not an explosion like that. It was a space explosion. There was no space and time before the Big Bang, according to standard models. There was no such thing as before. As a result, the Big Bang was unlike any other explosion we've ever seen, and it didn't require a center point. We would be able to observe the spreading edge of the explosion with empty space beyond if the Big Bang were a regular explosion in an already existent space. Instead, we look back to the Big Bang and observe a faint background light from the early universe's heated primordial gases. In all directions, this cosmic microwave background radiation is uniform. This means that rather than matter extending outwards from a point, space itself expands equally. Other findings, at least to the extent that observations can reach, support the concept that there is no center to the universe. Although the fact that the universe is expanding uniformly does not rule out the idea of a denser, hotter center, detailed studies of the distribution and motion of galaxies show that it is equal on the biggest scales we can observe, with no hint of a specific spot to designate the center. The cosmological principle, which states that no point in the world is exceptional, is compatible with the fact that the cosmos has no center, and, by extension, no boundary. Observations of galaxy cluster distribution and the cosmic microwave background indicate a cosmos that looks the same everywhere when zoomed out far enough. Humans have mistakenly believed we were at or near the center of the universe throughout history, whether that center was indeed the Earth, the Sun, or even the Milky Way galaxy. But, no matter how unique we humans believe we are, the cosmos has proven us wrong thus far. Do you believe the universe has a center? Let us know in the comments.